Alright, here's quiz 1 solutions. We start out question number 1. We're given a function f of x and we're asked to find the limit as x approaches negative infinity of f of x. As you may remember, when we're trying to find the limit as x approaches infinity or negative infinity, that's a similar question to trying to find where is the horizontal asymptote of this function. To figure that out, we take advantage of the fact that as x approaches negative infinity, this function we have, f of x, is going to act like, maybe that should be put into quotations, it's going to act like negative 5x squared over 2x squared. The logic behind that is when x gets really, really large or really large negative, the x squared terms, the term with the biggest degree, is going to be so much bigger than these terms over here with smaller degrees that they're going to kind of overpower them, so the function will be close enough to this function for our purposes. And the nice thing about this function right here is we can cancel out the x squareds and say that's equal to negative 5 over 2. So what that tells us is that this function has a horizontal asymptote at negative 5 halves. In other words, as x approaches negative infinity, f of x approaches negative 5 halves. Moving on to part B. Part B, we're given that f has a hole. We want to know where is it and what is the limit as we approach that hole. Okay, I rewrote f down here just so we'd have it on the screen. Remember, a hole are the x values that make the numerator and the denominator equal to 0. Kind of hard to tell what those are just by looking at this function, but what we can do is factor out the top and the bottom and see if we can find a common factor in there that will make both the top and the bottom 0. So I think the best way to factor the top, maybe we can take out at least an x, maybe a 5x. I kind of prefer to take out a negative 5x, although it's completely fine if you'd rather just take out a 5x, you'll end up with the same answer. Negative 5x, if we pull that out, we're left with x minus 1. If you have a little bit trouble seeing going from this direction to this direction, from the red to the blue, maybe it's easier for you to see going from the blue back to the red to check your work. Factoring out the bottom, it's easier to factor. I mean, we can always use the quadratic equation, but it's easier to factor if we have a leading coefficient here of 1. So to get that, we can take advantage of the fact that each of these terms are divisible by 2. So if we factor out a 2, we'd be left with x squared plus x minus 2. And let's see, x squared plus x minus 2 means we need two numbers that multiply to negative 2 and add to positive 1. Think about that for a little while. I think you'll come up with x minus 1 and x plus 2. And now we have this nice factored form. We can see we have this x minus 1 on the top and the bottom. So if you plug in a 1 for x, we'd end up with 0 over 0. Therefore, f has a hole at x equals 1. Part B here, we're asked for the limit as x approaches 1 of f of x. The way we can figure that out is by looking at our factored form of f of x here, which is equal to the limit as x approaches 1 of negative 5x over 2 times x plus 2. The advantage to this form is that we can now plug in 1 for x and not end up with 0 over 0. If you plug in 1 for x, you'll get negative 5 divided by 2 times 1 plus 2, 2 times 3, 6. So the limit as f approaches 1, as x approaches 1 of f of x is negative 5/6. Takes care of part B. Moving on to part C, I rewrote f of x again and copied down the factored form that we came up with in part B. In part C, it's asking about a vertical asymptote. Vertical asymptote happens when the denominator is equal to 0 but the numerator is not. As you can see from the factored form, this will happen when x equals negative 2. So we have our answer that the vertical asymptote happens at x equals -2. And then we're asked for the limit as x approaches -2. See, it says from the left, so we'll want -2 minus of f of x. Since we know it's a vertical asymptote, our answer will either be infinity or negative infinity, so really all we have to do here is keep track of the sign. So maybe this equal should be in quotation marks here, but one way to take care of this problem is just to look at each of these factors here and think about whether they'll be negative or positive if we plug in a number a little bit less than -2. See, a little less than -2, we're thinking -2.0001-ish. So let's see, if we plug in a number a little bit less than -2, -5x times -2 will give us a positive number. -2 minus one more, definitely going to be negative. 2 is always positive. -2 minus 1 again is negative. Could have canceled out these two factors before we did this analysis. We wouldn't have these two guys here. Won't change the answer at all. This last one's the hardest one. Let's see, -2 plus 2 is going to be negative because we're a little bit less than -2 here. And that'll leave us with a negative number divided by a positive number, right? Negative times negative is a positive, which is a negative. So therefore this limit is equal to negative infinity. Moving on to question 2. Okay, in this question we're asked to evaluate the limit as x approaches 10 of this expression. Hopefully that looks a little bit familiar. Looks something like a homework problem we did. Unfortunately, we can't just plug in 10 for x everywhere. We'd end up with 0 over 0. Seems to always be the case in these types of problems. So what we'll have to do is cancel out this x minus 10 with an x minus 10 from the bottom here. It's not immediately apparent where that x minus 10 comes from, but if we simplify some, we'll be able to pull one out. I think the first thing you'll want to do is find a common denominator for the bottom of our big fraction here, the denominator of the bigger fraction. That common denominator will be 10x, which we get by multiplying this term by 10 over 10, and this term by x over x. And what that gives us is the limit as x approaches 10 of x minus 10. Maybe instead of just writing x minus 10, I'll call it x minus 10 over 1, so that we can keep track of our fractions inside fractions. On the bottom, we'll have 10 minus x divided by our common denominator of 10x. And now we can get rid of this fraction inside of a fraction nonsense. The way you divide fractions is just like multiplying fractions, except you have to multiply by the reciprocal of the denominator here. Flip this guy upside down. So we get the limit as x approaches 10 of x minus 10 over 1 times the reciprocal of the denominator. We're starting to look a little bit better. You can almost cancel these guys out, but not quite. A common mistake was to cancel them out immediately, but x minus 10 is different than 10 minus x. However, what maybe you'll notice, or maybe you remember from the homework, is that if we pull out a -1 down here, this will turn into -10 plus x, which is the same as x minus 10. So we can rewrite this expression as the limit as x approaches 10 of x minus 10 over 1 times 10x divided by -1 times x minus 10. Which is good because now we get one of the more satisfying feelings in math when you get to cancel out terms like this. And our limit simplifies into the limit as x approaches 10 of 10x over -1, which if we plug in 10 for x, we get 100 over -1, in other words, -100, which is our answer. So there's the solutions to quiz 1. I'll post these on Blackboard. Hope that that is helpful.